On March 14, 2025, the James Webb Space Telescope detected something that shouldn't exist. A planet 124 light-years from Earth, so distant that the light we're seeing left before your great-great-great-great-grandparents were born, with atmospheric chemistry that screams life. Here's the paradox. Despite observing a world we could never physically visit in 1,000 human lifetimes, Webb has measured its air composition with such precision that astrobiologists are now arguing not if life exists there, but what kind. The planet is called K2-18b, and the data coming back is forcing us to rewrite the rules of habitability. How is it possible to smell the air of an alien world from 1.2 quadrillion kilometers away? And how much longer can Webb keep probing the atmospheres of distant worlds before its consumables run out? The James Webb Space Telescope launched on December 25, 2021, atop an Ariane 5 rocket from French Guiana. But here's the counterintuitive detail. Webb wasn't originally designed to hunt for life. Its primary mission targeted the universe's first galaxies, light from stars that formed just 200 million years after the Big Bang. To see that ancient red-shifted light required infrared sensitivity and a mirror so large it had to fold like origami to fit in the rocket. Exoplanet atmospheres were a secondary goal, a bonus science case to justify the $10 billion price tag to skeptical politicians. But a special circumstance changed everything. In 2017, astronomers using Hubble and Spitzer detected water vapor in K2-18b's atmosphere, the first time water had been confirmed on a potentially habitable exoplanet. The planet orbited a cool M-dwarf star in the constellation Leo, passing in front of, its star every 33 days. That transit geometry was the key. When K2-18b passed between us and its star, a tiny fraction of starlight filtered through the planet's atmosphere. Molecules in that atmosphere absorbed specific wavelengths, leaving fingerprints Webb could read. Webb's infrared eyes were perfectly tuned to catch those fingerprints. 5 key achievements established K2-18b as extraordinary. Achievement 1. Water vapor confirmation. Webb's NIR-SPEC instrument detected strong water absorption at 1.4, 1.9, and 2.7 microns. 3 independent wavelength bands, all screaming H2O. Not trace amounts. Abundant water vapor. Achievement 2. Methane detection. Methane showed up at 3.3 microns. On Earth, the vast majority of atmospheric methane is biological, produced by microbes, wetlands, and, yes, cow digestion. Finding it on K2-18b was the first red flag. Achievement 3. The missing carbon dioxide. Here's where it got strange. K2-18b's atmosphere showed less CO2 than models predicted for a sterile, hydrogen-rich world. Something was removing it. On Earth, that something is photosynthesis and ocean absorption driven by life. Achievement 4. Dimethyl sulfide hint, the most controversial detection, a tentative signal at 3.5 microns consistent with dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton. It's so strongly associated with biology that finding it elsewhere would be a smoking gun. Achievement 5. The Hycean world hypothesis. Match. K2-18b's mass, 8.6 Earth masses, radius, 2.6 Earth radii, and orbital position in the habitable zone matched predictions for a Hycean world, a hydrogen-rich atmosphere over a liquid water ocean, a completely new class of potentially habitable planet we'd only theorized about until Webb looked. 2 telescopes, 2 completely different windows into K2-18b. Each revealed what the other couldn't. Hubble's path, the Hubble Space Telescope, launched in 1990, observed K2-18b in visible and near-infrared wavelengths. It detected water vapor in 2019, a historic first. But Hubble's instruments lacked the sensitivity and wavelength coverage to probe deeper. It saw the surface of the mystery, but couldn't read the details. Hubble also observed K2-18b sporadically, grabbing transits when scheduling aligned, and its aging instruments were available. As Hubble's gyroscopes failed and its orbit slowly decayed, exoplanet science became a lower priority. Webb's path. Webb, positioned at the L2 Lagrange point 1 million miles from Earth, can stare at targets for weeks without interruption. Its 6.5-meter segmented mirror, roughly 6.25 times Hubble's collecting area, gathers infrared photons with ruthless efficiency. Webb observed K2-18b for over 27 hours across 2 separate transits, building up signal-to-noise ratios Hubble could never dream of. It measured not just water, but the isotopic ratio of hydrogen in that water, the methane to CO2 balance, and hunted for biosignature molecules at parts per million sensitivity. Current status comparison. Hubble, 34 years in orbit, running on degraded gyroscopes and aging instruments, expected to deorbit sometime between 2030-2040. Webb, 3+ years operational, propellant reserves sufficient for 20+ years, all instruments functioning nominally. Here's the relativity trick. A 27-hour observation block may not seem like much, just over a day of staring. But imagine if a doctor could scan your entire body, down to individual cells, in 27 hours from across the street, through walls, without you ever knowing they were watching. That's what Webb just did to an alien world 124 light-years away. What Hubble achieved proved exoplanet atmosphere science was possible. Detected water on K2-18b, paved the way. What Webb achieved turned exoplanet atmospheres from barely detectable to chemically dissectable. Found tentative biosignatures. The difference isn't incremental, it's categorical. 2 commonly confused terms: habitable zone versus habitability. Think of the habitable zone as a distance range from a star where liquid water could exist on a planet's surface. Not too hot, water boils away. Not too cold, water freezes solid. It's a simple temperature calculation based on the star's luminosity. For our Sun, the habitable zone runs from about 0.95 to 1.37 AU. Venus is too close, Mars is near the outer edge, Earth is comfortably in the middle. For K2-18 star, a cool M dwarf putting out just 2.5% of the Sun's light, the habitable zone is much closer in, 0.13 to 0.25 AU. K2-18b orbits at 0.14 AU, barely inside the inner edge. But here's the critical distinction. Being in the habitable zone doesn't guarantee habitability. Think of habitability as the full checklist: liquid water, stable atmosphere, protective magnetic field, the right atmospheric pressure, a non-lethal radiation environment, stable climate over geological time, and, crucially, atmospheric chemistry that permits life as we know it or as we can imagine it. Venus is in the Sun's habitable zone. It's a 400 to 70-degree hellscape with sulfuric acid clouds. K2-18b is in its star's habitable zone, and its atmospheric chemistry looks suspiciously alive. The exact moment of transition, when K2-18b went from interesting to potentially inhabited, came when Webb's second observing campaign in late 2024 added the DMS detection. Timeline context: 2015, K2-18b discovered by the Kepler K2 mission as a transiting exoplanet candidate. 2019, Hubble detects water vapor, first confirmed H2O on a habitable zone exoplanet. 2023, JWST observes K2-18b for the first time, confirms water and methane, notes missing CO2. 2024, follow-up JWST observations add tentative DMS detection and measure atmospheric methane isotope ratios inconsistent with purely geological sources. 2025, multiple independent research teams publish analyses. The consensus shifts from interesting atmosphere to plausible biosignatures detected. The significance, if DMS is confirmed, and that's a big if, requiring more observation time, it would be the first molecule detected on an exoplanet with no known abiotic, non-living production pathway at the concentrations measured. We'd have found life's calling card, written in chemistry, across 124 light-years of space. Restate the core mystery. How does a telescope 1 million miles from Earth read the chemical composition of an atmosphere on a planet 124 light-years away? A world so distant, its light takes 124 years to reach us? The answer lies in transmission spectroscopy, a technique so elegant it feels like cheating. When K2-18b transits its star, it blocks a tiny fraction of the star's light, about 0.6%. Most of that blocked light simply hits the planet's solid or liquid surface and is absorbed. But a razor-thin shell around the planet's edge is atmosphere. Starlight passes through that atmospheric shell. Molecules in the atmosphere absorb specific wavelengths based on their quantum energy levels. Water absorbs strongly in the infrared near 1.4, 1.9, and 2.7 microns. Methane absorbs at 3.3 microns. DMS, if present, absorbs around 3.5 microns. What reaches Webb isn't a uniform spectrum. It's starlight with tiny bite marks taken out of it by K2-18b's air. Webb's detectors measure those bite marks with extraordinary precision. The transmitter analogy. Think of K2-18b's atmosphere as a chemical barcode. The star is the backlight. The planet passing in front is the scanner reading the barcode. Webb is the computer decoding the result. Signal travel time perspective ladder. Layer 1. Light leaves K2-18's star and travels 8 million kilometers to reach K2-18b's atmosphere. Travel time, roughly 27 seconds. Layer 2. That filtered light then travels 124 light-years across interstellar space to reach the solar system. Travel time, 124 years. The photons Webb captured in 2023 left K2-18 system in 1899. Layer 3, Webb is not at Earth, it's at L2, 1 million miles away. Commands from Earth take 5 seconds to reach Webb. Data returns take another 5 seconds. During K2-18b observations, mission controllers send commands that will collect photons that left their source over a century ago, with a 10-second Earth-Webb communication lag layered on top. Signal degradation by physical law. Light spreads out as it travels. Intensity falls with the square of distance. K2-18 is 124 light-years away, roughly 1.17 x 1015 kilometers. By the inverse square law, the light reaching us is diminished by a factor of about 1.4 x 1030 compared to the intensity at K2-18b's distance from its star. To put that in perspective, if K2-18 star were a 100-watt light bulb, by the time its light reaches Webb, each square meter of Webb's mirror collects the equivalent of a few trillion photons per second during transit. That sounds like a lot, but Webb's detectors are counting individual photons in specific narrow wavelength bins. The methane signal might be just a 0.01% change in brightness in one specific infrared channel, requiring hours of integration to detect above noise. How massive the receiver must be! Webb's primary mirror, 6.5 meters across, 25 square meters of collecting area. To detect K2-18b's atmospheric signals with statistical significance, you need to gather millions of photons per wavelength channel. Webb's NIR-SPEC instrument splits incoming light into hundreds of narrow wavelength bins, each collecting photons separately. Smaller mirrors couldn't do this. Hubble tried and barely succeeded. Ground-based telescopes are blocked by Earth's atmosphere, which absorbs the exact same infrared wavelengths Webb is hunting for. Only Webb, and future space telescopes like the proposed Habitable Worlds Observatory can play this game. The global network, Webb's data downlinks through NASA's Deep Space Network, 3 complexes of massive radio dishes in California, Spain, and Australia, positioned around Earth to ensure 24/7 line of sight to L2. Each downlink session transfers up to 57 gigabytes. A single K2-18b observation campaign generates terabytes of raw data, which teams of scientists spend months processing, calibrating, and analyzing. Finding biosignatures isn't a single aha moment. It's a slow, methodical assembly of evidence, photon by photon, spectrum by spectrum, observation by observation. Here's why the normal solution doesn't work. Webb cannot be refueled or serviced. Hubble sat in low Earth orbit, reachable by space shuttle. Astronauts visited 5 times, upgrading instruments and replacing failing components. Webb is at L2, 1 million miles away, 4 times the distance to the Moon. No current spacecraft can reach it. It was designed to be a one-shot mission, work until something critical fails or the fuel runs out, then drift into an independent solar orbit as a derelict monument. The limiting consumable: hydrazine propellant for station-keeping thrusters. Webb must perform small burns every few weeks to maintain its delicate halo orbit around L2 and to manage angular momentum, offloading the reaction wheels that rotate the telescope. Starting capacity: 240 liters of hydrazine, budgeted for a 10-year mission. Current capacity as of early 2025, approximately 210 liters remaining, about 87.5% of the original load. Why more than expected? The Ariane 5 rocket performed its insertion burn with such precision that Webb needed far less fuel than worst-case scenarios for the journey to L2. Mission planners now project 20-plus years of operation instead of the original 10-year baseline. Conservation measures: reaction wheel momentum management. Webb uses internal flywheels for most attitude changes, saving thruster fuel for only when wheels saturate. Optimized observation scheduling. Science operations are sequenced to minimize fuel-expensive telescope slews. Passive thermal stability. The sun shield keeps instruments cold without active refrigeration, except for MIRI's dedicated cryo-cooler, reducing thermal expansion corrections. Emotional artifact with finality. There will come a day, perhaps in the early 2040s, when mission controllers uplink the final observation sequence. Webb will point at some distant galaxy, exoplanet, or stellar nursery one last time. The data will transmit back to Earth. Then, with fuel reserves exhausted, Webb will begin to drift. Its orbit will slowly decay under the subtle gravitational tugs of Earth, Moon, and Sun. Within a few years, it will fall into an independent heliocentric orbit, becoming a silent artifact carrying humanity's names, etched on a microchip during construction, through the cosmos indefinitely. Current minimal operations. As of 2025, Webb operates at 100% science efficiency. No fuel is reserved for potential servicing missions that will never come. Every observation is made with the knowledge that the fuel budget is finite and irreplaceable. Projected declining trajectory. Current best estimate: fuel depletion between 2040–2045, depending on how aggressively reaction wheels are used versus thrusters. After that, Webb goes silent. Every K2-18b observation, every distant galaxy image, every exoplanet atmosphere study, they all exist within this shrinking window. Problem 1. The micrometeoroid strike, May 2022. 5 months into science operations, a micrometeoroid, smaller than a grain of sand, traveling roughly 20,000 km, struck mirror segment C3 on the lower right of Webb's primary mirror. Why it's critical? Even microscopic damage creates optical aberrations. The impact left a permanent 5-micron crater in the gold coating and beryllium substrate. That segment now slightly misfocuses starlight. Automated solution. Within hours, Webb's wavefront sensing software detected the aberration. The onboard computer commanded segment C3's actuators to adjust position and curvature by nanometers, compensating for the deformation. Resolution. 2 weeks later, overall image quality returned to 99% of pre-impact performance. The scar remains, but realignment minimized its effect. Ongoing threat. 5 more strikes have occurred since. Statistical models now predict 1 detectable impact every 2 months. 4x faster than pre-launch estimates. Each hit adds permanent, unrepairable damage. K2-18b implication. Micrometeoroid degradation will eventually limit Webb's ability to perform ultra-precise transmission spectroscopy. Every strike slightly blurs the mirror's focus, making faint spectral features harder to detect. Problem 2. The MIRI Grating Wheel Friction Anomaly. August 2022. Webb's mid-infrared instrument. MIRI, critical for detecting molecules like methane and DMS at 3 to 5 micron wavelengths, began showing increased friction in its internal grating wheel. The wheel rotates to position different diffraction gratings in the optical path, enabling spectroscopy across MIRI's wavelength range. At operating temperatures of 266 degrees, lubricants behave unpredictably. Why it's critical? If the wheel mechanism seizes, an entire observation mode fails permanently. MIRI's medium-resolution spectroscopy mode, the exact mode used to hunt for DMS on K2-18b, would be lost. Diagnosis: 3 months of remote testing across the 5-second Earth-Webb signal delay. Engineers discovered certain grating positions, 15° to 25° rotation, caused excessive friction. Manual fix. New operational procedures avoid the high-friction zone. MIRI observations now use longer exposures with the wheel held in stable positions, rather than continuous rotation. Resolution. As of 2025, MIRI operates in all modes using adapted procedures. The wheel shows no further degradation, but progressive wear is inevitable. K2-18b implication. Future DMS confirmation observations depend entirely on MIRI continuing to function. If the grating wheel fails, no other Webb instrument can detect DMS. Future problem 3. The anticipated detector degradation 2030s. Webb's infrared detectors, sensitive HGCDTE, mercury-cadmium telluride, arrays, are gradually accumulating radiation damage from cosmic rays. Proactive monitoring. Engineers track hot pixels and sensitivity drift in each detector. Onboard software compensates by flagging damaged pixels and using adjacent ones. Anticipated solution: there is no hardware fix. Software calibration can mask detector damage up to a point. Beyond roughly 15 to 20 years, accumulated damage may degrade sensitivity below usable thresholds for faint targets like exoplanet atmospheres. Expected extension: if detectors degrade slower than models predict, Webb could continue exoplanet science into the early 2040s. If degradation accelerates, that window closes sooner. K2-18b implication. Follow-up observations to confirm DMS and hunt for other biosignatures must happen soon, ideally within the next 5 to 10 years, while Webb's instruments remain sharp. Ongoing challenges compound with every passing year. Micrometeoroid impacts accumulating permanent mirror damage. Reaction wheel bearings experiencing micro-wear from millions of rotation cycles. Cosmic rays degrading detector sensitivity, propellant depleting with every station-keeping burn. Mission planners currently project fuel exhaustion in 2043, 22 years post-launch. Time remaining from 2025, 18 years at most. That assumes no catastrophic sunshield tears from debris impacts, no instrument failures beyond current workarounds, no unexpected propellant leaks, no solar panel degradation exceeding models. Every K2 to 18b observation, every spectral line, every tentative biosignature molecule, every follow-up campaign to confirm DMS exists within this contracting window. Sometime in the early 2040s, ground controllers will transmit the final command sequence. Webb will execute its last observation, perhaps one final look at K2-18b, documenting how its atmosphere has changed over 2 decades. The data will crawl across 1 million miles at light speed, 5.3 seconds to reach Earth. Then, silence. K2-18b will continue orbiting its dim red star every 33 days. Its atmosphere will keep churning, potentially teeming with microbial life producing methane and DMS. But humanity will stop watching. Our window into that alien world will close, and we'll be left analyzing data archives, trying to squeeze every last insight from observations we can never repeat. The clock is ticking, not just for Webb, for our chance to answer the oldest question. Are we alone? Webb launched December 25, 2021, designed for a 10-year minimum mission. It may survive 22 years. Compare its specs to modern tech. Data storage, 68 GB solid-state memory, less than a budget smartphone. Processing power, 25 Vitamin-Thebit processors, slower than a 1990s desktop. Downlink speed, 28 Mbps, slower than average home internet. Mirror accuracy, 10 nanometer alignment precision, 30,000x better than LASIK surgery. The paradox epitomized, ancient computational technology, yet the most sophisticated astronomical instrument ever deployed. Webb didn't just find K2-18b's atmosphere interesting, it potentially found life's chemical fingerprints written in an alien sky. If DMS is real, if methane is biological, if the missing CO2 means photosynthesis. Those are big ifs, but they're ifs we can now ask with data, not speculation. Webb will continue staring at K2-18b and hundreds of other worlds, building the first census of exoplanet atmospheres until its fuel runs dry. After that, it drifts into a solar orbit, carrying our hopes and questions into the endless dark. But K2-18b will still be there, still orbiting, still potentially alive, waiting for the next telescope, the next generation, the next chance to hear what it's trying to tell us.